Hello guys, and welcome to Team 7's presentation for the MSc 4793 final project, which is over dental composites. In this presentation, we will discuss the many aspects of dental composite manufacturing, including the origins of dental composites, the details of manufacture of modern dental composites, and the continuing improvements that are made today. Each year, 5 million people receive a dental implant to improve dental hygiene and smiles. The ultimate goal for the composite is to replace the dental root. The desired composite characteristics for a dental implant application include biocompatibility, chemical resistance, high corrosion resistance, durability, and to be aesthetically pleasing. Resin composites increased in popularity over amalgams, an alloy of mercury, in 1999 due to their improved mechanical properties and white coloring. The dental composites showed significant advantages in strength and durability over the prior metal implants and were much less damaging for the mouth. Thus, the ultimate goal of this presentation is to demonstrate how composites are the ideal material to produce dental implants with and provide much strength and wear resistance. Early civilizations used carved ivory and gold ligature wire to restore natural teeth. Continuing into the modern era, metal implants as a whole became mainstream in the early 1900s. Fast forwarding to the 1980s, silver amalgams became the most frequently used restorative dental material. But it was found that when patients chewed, mercury vapor was released, which is very toxic to the body. Additionally, the silver was not aesthetic. Today, dental composites are utilized for their superior mechanical properties, biocompatibility, and aesthetic nature. Dental composites are used to replace the structure of missing tooth material. This can be in the form of cavity fillings or implants. Dental composite resins are composed of an organic polymer matrix, inorganic filler particles, coupling agents, and an initiator-accelerator system. Some common organic matrix materials include bis-TMA, PEG-DMA, UDMA, and bis-EMA. For this presentation, the focus will be placed on UDMA, or urethane dimethylcrylate matrices. Dental composites must meet certain performance requirements to ensure their effectiveness in tooth restorations. These requirements encompass mechanical, aesthetic, biocompatibility, and longevity factors. Mechanically, composites need sufficient flexural and compressive strength, along with abrasion resistance to withstand oral forces. Aesthetically, they must mimic natural teeth in color, opacity, and surface finish. Biocompatibility is crucial to prevent adverse reactions in oral tissues, requiring non-toxicity, tissue compatibility, and low water absorption. Additionally, composites should exhibit longevity by resisting degradation and maintaining marginal integrity. Finally, favorable handling characteristics such as viscosity, curing time, and adhesive properties are essential for easy manipulation by dentists. Meeting these criteria ensures that dental composites provide durable, aesthetically pleasing restorations while promoting oral health. Some raw materials to produce our dental composite include the following: UDMA as the organic polymer matrix, as shown in Figure 2. NACP and etc. are inorganic additives to prevent disease and bacteria from attaching to the composite. And the silane coupling agent is used to increase chemical interfacial adhesion, as shown in Figure 3. UDMA, urethane dimethylcrylate, will be analyzed in its application to dental implants, as it has the highest rate of polymerization, low viscosity, and flexibility. UDMA has a dense polymer network in comparison to TGMA and bis-TMA. Polymerization shrinkage, modulus of elasticity, and solubility are the largest problems associated with the organic polymer matrix. Inorganic filler particles are added to the polymer to prevent disease and bacterial attachment. Common inorganic additives to UDMA include NACP, CAF2, BAG, HA, FA, and BN. Depending on amounts of additives, the properties shift slightly. It is very important for the pH balance to be maintained, as mineral loss is initiated at 6 to 6.8 pH in the root and 5.4 pH in the enamel. In order to increase the mechanical properties of the polymer matrix with inorganic filler particles, nylon coupling agent increases the chemical interfacial adhesion. Surface pretreatment is necessary to ensure durable bonding to the resin. Lastly, the initiator-accelerator system cures the composite by utilizing a chemical reaction or light. All of these aspects combined allow composites to be the ideal material for dental implants due to the properties listed in the image including, but not limited to, biocompatibility and mechanical properties. While the bulk of the composite structure is the organic polymer matrix, there are other components as mentioned in the prior slide. The organic matrix forms the base of the structure of the composite. UDMA has an aliphatic core, thus it is organic, with urethane links which allow the molecule to form hydrogen bonds. It is formed of a filler phase and a matrix phase. For the matrix portion, the urethane bonds give the molecule flexibility, allowing it to be a tougher material. Depending on the packing of the atoms in the compound, there is a different type of fill. Thus, for the filler phase, microhybrid composites are typically stronger than microfilled composites and can be used in both anterior and posterior teeth. Hybrid composites are filled 70 to 80% by weight with 0.04 micron meter and 1 to 5 micron meter filler particles. It is highly polishable and typically has medium viscosity. Microfilled composites have higher coefficients of thermal expansion, high viscosity, greater polymerization shrinkage, lower tensile strength, and lower fracture toughness. Nanofilled composites have even greater properties because of the packing associated. The optimal criteria for an organic polymer matrix is one that has high polishability, good mechanical properties, translucency, and fluorescence. While the bulk of the composite structure is the organic polymer matrix, there are other components as mentioned in the prior slide. The organic matrix forms the base of the structure of the composite. To manufacture the composite, the following steps occur. First, there is polymerization, where the organic polymer matrix, along with any additives and coupling agents, is mixed together to form a composite resin. In step 2, the inorganic filler particles are added to the resin mixture. The amount of filler particles can be adjusted based on the desired properties of the final composite. After that, the surfaces are treated to ensure proper bonding before application. The final step in the manufacturing process is curing. This is when the initiator-accelerator system is activated, either chemically or with light, to initiate the curing process. This process solidifies the composite material into its final form. The cost for users of restorative dental procedures is highly dependent on the time commitment and material cost for composite resin fillings. In terms of material costs, the price is mainly reliant on the type and depth of the cavity, with the branched resin playing a minor role in total cost. Average direct material costs for composite fillings were approximately $8, which includes procedure equipment and the resin itself. For the user, composite resin fillings can cost anywhere from $100 to $500 per tooth. These costs depend highly on the complexity of the procedure. The global dental composites market value in 2022 is valued at $59.7 billion, with projections to reach over $100.4 million by 2031. The market for composite dental work is widespread and only growing. The main market includes dental professionals, labs, and patients. Dental professionals primarily use composite resins for implants, crowns, and bridges, and dental labs fabricate restorations using composite materials. Patient motivation involves seeking a durable, natural-looking implant or filing for dental restoration procedures. Major manufacturers of dental composite products include Ivoclar, Vita, 3D Systems, Dentsply Sirona, and Care. These companies and more are furthering research and development of these products in both materials and innovative technologies. New developments related to dental composites include new resin formulations and improved processes that minimize the release of monomers from the dental materials. In choosing a resin for dental composites, factors to be considered include viscosity, degree of monomer conversion to polymer, polymerization shrinkage, water absorption, and mechanical strength. These factors determine the ease of application and how quickly a dental composite will be degraded in daily use. Degradation of dental composites is an important focus in research, as the breakdown of the resins can release harmful monomers into the user's body. To combat this, a novel resin was formulated with better mechanical properties than current dental formulations. This resin is an MEBDI-based urethane dimethacrylate resin with TEGDMA. Further research into the functionality and feasibility of this formulation must be done in the future. In terms of processes, the type of light source used for photopolymerization, or curing, as well as the time the resin was left to cure, are important in decreasing the amount of harmful monomers being released by the degradation of the dental composite. Studies revealed that the best time this results for limiting degradation were found with longer resin cure times and the use of a diode lamp as opposed to a halogen lamp for activation. Dental composite resins are the most widely used restorative dental material. These resins are able to restore the physical integrity of damaged teeth, most commonly through fillings or implants. When compared to other dental restoration materials, composite resins have a higher degree of wear resistance and less shrinkage, which can lead to product failure. Another benefit of composite resins is the natural aesthetics they provide, as they are available in a range of colors. However, research is still needed in improving these materials, as they are still prone to failure through shrinkage and adhesive failure. Another major concern that must be addressed is the potential for user exposure to harmful monomers as the resins degrade over time. In conclusion, modern dental composites are truly the way to go for dental applications. Perhaps there will be a better application found in the future, but as of right now, composites are the way to go. Here are some sources we used for our presentation, and I hope that you guys have a wonderful day and learned a lot about dental composites.